Hi, everyone. Welcome to Cloud Engineering and Practice. Thanks for joining us today. So today we'll be talking about the various efforts underway to achieve intensive data processing by infusing cloud technologies into software infrastructure. We'll be sharing our experiences and some of our lessons learned. We do have remote participation available for this, like all the other sessions. So please do wait to get the microphone so remote participants can hear your questions. And this session is being recorded and will be archived for future viewing. Our first talk we have is Steering the Ship, Making Sense of Multi-Container Deployments with the Help of Kubernetes and AWS by Frank Gorguska. Frank is a software engineer at NASA's Jet Propulsion Laboratory. He is currently working on the NASA Sea Level Change Portal, among other projects. He has his bachelor's in software engineering from the Milwaukee School of Engineering and has over 9 years of software engineering experience. In high school, he was voted most likely to produce cloud-optimized analysis-ready data. So I'm going to invite Frank.
Thank you. Going all the way back to high school, you did your research on me. So let me get my slides up here. Okay. Does the GoToMeeting look okay? I think we set it up. Is anyone on it? Looks good? Okay, thank you. So yeah, I'm going to talk about steering the ship and using Kubernetes to deploy a cloud-ready application, specifically that runs the NASA Sea Level Change Portal running on AWS in the EKS web service. So what I'm going to talk about first is why Kubernetes. So I guess I want to level set here real quick and just kind of get a show of hands in the room. Who's actually heard of Kubernetes before? Okay, that's pretty good then. How many people have actually used Kubernetes? Okay, a few less people. Okay, anybody use EKS? Okay, maybe like 2 people. Okay, that's good. So the first kind of half the talk is going to kind of set the stage for why we use Kubernetes, where it kind of fits in the overall ecosystem. A pretty quick crash course into Kubernetes, the different main components of it, and kind of the domain language that's used when you're deploying applications via Kubernetes. And then I'm going to get in depth into how we actually structured and deployed the backend for the NASA Sea Level Change Portal to Amazon's EKS service. So first of all, why do we need Kubernetes? Okay, first there's been Docker, right, and containerization. It's taken off over the last few years. It's everywhere, right? And containers are more or less, you can think of them as like VMs, right? You might be familiar with this kind of a diagram where all the way on my right, your left, is kind of the traditional deployment where you're deploying to a server. You know, you have your hardware, your operating system, and you deploy your applications to that. Virtualization came along with VMs, and that kind of abstracted that a little bit, where you share the hardware and the operating system. Then there's an abstraction of the hypervisor, and then you can kind of segregate things that way. Containers take it one step further, where the hardware and the operating system are shared still, and then the container runtime is on top of that, and you can deploy more applications to the same hardware as opposed to the case of VMs. The issue with this, or I guess not necessarily an issue, but the thing to remember is for containers, the best practice is to deploy one process per container, essentially. So one container runs one application or one process. So what happens then when you're in a situation where you have a software application that contains many processes, right? How do you then deal with that case? Well, Docker's answer to that is Docker Compose, right? It's essentially a YAML file that describes your different Docker containers, and it lets you launch multiple containers onto one piece of hardware. Sorry, not sure. There we go. Sorry, it looks like someone took over the screen and started sharing something else. Okay, we're good. So that's kind of the answer that Docker has. It's Docker Compose, but you're still constrained to, essentially one piece of hardware at that point. So, okay, that's good. That gets us one step further. We're now beyond just one process, but we're still locked down to one machine. So now how do we deploy many containers across many machines? This requires another higher level of orchestration in order to do that. And there's a couple of different technologies out there. So Docker Swarm is one technology that is created from the Docker team that can actually do this as well. It's a way of orchestrating and farming containers out across a cluster of machines. And then Kubernetes is an alternative. Kubernetes is an open source project. It started with Google, and it's been gaining a lot of popularity over the last few years. And actually, interestingly, Docker Swarm has a plugin to actually let you use Kubernetes as kind of the implementation of Docker Swarm as well. So even the Docker team acknowledges the gorilla in the room that is Kubernetes. So I want to talk briefly about kind of the main components of Kubernetes. But for now, we're just going to ignore the cloud part up there. We'll get to that part later. So the way that Kubernetes essentially works and does all of this, it's split into essentially two main components that you can see here. On one side, we have the Kubernetes master components. You also hear me refer to that as the control plane. It's essentially the same thing, but it consists of a few different components itself. One of the main entry points into Kubernetes is the API server. The API server is essentially the interface into everything. So it lets you deploy your applications, it lets you manage your cluster, set up your nodes, do all of those things. One important thing to remember for the API server is any request coming into the API server has to be authenticated. So that becomes important later when we start talking about the cloud deployment and how you lock it down and security concerns and things like that. The scheduler is responsible for actually scheduling the containers and the deployments out to the different machines. The controller manager is essentially the control loop for Kubernetes. So it's the thing that's essentially constantly looking at the current state of the system and making sure that it matches what the desired or expected state of the system is. So that's kind of the high level there. And then the other side, apart from the control plane, is the minions or the Kubernetes workers. Okay, and those are essentially the servers where your applications actually run. The main thing that enables this, there's two components that run there, the kubelet and the kube proxy. You don't need to know too much details about that. Essentially, the kubelet is what deploys the containers onto the node and manages that stuff. The kube proxy enables the network communication that we're going to see that you can set up from Kubernetes. So that's kind of the high-level architecture of Kubernetes and kind of how it gets things to work. But if we take a look inside of Kubernetes almost, this is where we start getting into kind of the domain language of Kubernetes. So I've been saying things like containers and things like that. Technically in Kubernetes, you don't deal with containers at all. You actually, the smallest unit of deployment is a pod, which you see here. A pod is actually, technically, it can be one or more containers, but they're grouped together, meaning that they have similar functions. A pod runs on one node. It has an IP address, things like that. The other things to remember is there's a number of different controllers that are available in Kubernetes, and each one is kind of used for a slightly different use case. The simplest one is just a deployment, which lets you have define a replica set, which essentially lets you farm out pods, identical pods across all of the nodes in your cluster. A daemon set is similar, but whereas a replica set doesn't have to run on every single one of your nodes in the cluster, a daemon set ensures that a version of the pod that you're deploying is running on every node at all times. So that's for things like your web servers or something like that, where you have a long-running process that you want on all of the available nodes in your cluster up all the time. There's also the stateful set, which is useful for applications that need to save state. So stateful sets are what you would want to use if you have to use like disk storage, block storage. It allows you to have an IP address that is the same every time that the application is deployed, things like that. And then job and cron job are used for short-lived processes. I say short-lived, I mean, it could be, hours or even days that it takes, but it's for those batch processing type workflows where it's not a web server that's always up and running. A few other things that Kubernetes kind of gives you an abstraction of are kind of listed up on top there. Service discovery, storage orchestration, rollouts, rollbacks. It's self-healing. It lets you manage configuration management. So all this stuff you kind of get out of the box with Kubernetes. So that's part of the reason why it's so popular, is because there's so much to this ecosystem. But that's also probably why it's so daunting to a lot of people, because the ecosystem is so large already. So if you want to learn more, I actually found this blog that's linked down on the bottom. It's a really good read. It's not too long. It kind of goes through some of these same concepts. So if this is kind of like piqued your interest and you're like, oh, that's interesting, I want to kind of learn a little bit more about these different things, I'd recommend go reading that blog, because I think it did a really good job of kind of summarizing. So Kubernetes, kind of taking a look at this cloud part now. Kubernetes can actually be deployed on bare metal servers, but it was also built to run on the cloud. And it actually has support from the three major cloud vendors that are out there: Amazon, Azure, and obviously Google. It's all kind of abstracted through this other component that we didn't mention on the control plane, which is the Cloud Controller Manager. And essentially, the different providers write implementations of this interface where their implementations take care of the idiosyncrasies and the differences between, for example, Amazon and Google. So it's kind of abstracted away. You don't have to worry about it. There are a ton of other hosted projects out there as well. This link, I kind of want to open it right now just to kind of give you an overview. This is crazy. I saw this. This is kind of a list of, oh, it's not the right one. This is a list of the cloud landscape at the moment. So it's kind of a collection of all the different services and hosted offerings of Kubernetes, all the technologies that go into it. and it kind of breaks it down into in an interesting way. This is the Cloud Native Computing Foundation, and it's just interesting to kind of look at this and just see all of the different technologies that are out there in this ecosystem. But, okay. So, okay, that's your Kubernetes crash course. So you're all Kubernetes experts now. Check that box. So now that we have kind of the background available, we want to talk about some of the concerns that are necessary to think about when you actually want to ship something like this out to production, right? So I'm going to talk through our application of it as applied for the NASA Sea Level Change Portal. So some of the concerns that you need to think about are your network isolation. So, you know, you're running a farm of servers essentially. Where are those servers running in terms of the network? How do you secure it? That type of a thing. Separation of environments. So do you need a SIT, you know, a test, QA, production, different environments, things like that. How you handle authentication and authorization, resource quotas and scaling, and then kind of those day two operations. So how do you handle patches, updates? How do you get insight into your cluster? What services are running? What applications are up or down? And then cost as well, obviously. We're talking about running on the cloud, so nothing's free. So let's get that out of the way. We're going to focus on AWS. This deployment that I'm going to go through is one architecture that can be done. There's so many options out there, as you know, you saw. So we're focusing on AWS and specifically Amazon's Elastic Kubernetes service. Essentially, it's a service that's provided by Amazon. And if you remember back to that diagram where we had the split between the minions and the control plane, essentially what EKS is, Amazon takes control of that control plane for you. So it manages all of those different components. It also handles doing patches and updates and things like that. So that's honestly one of the hardest parts of running a Kubernetes cluster. So having Amazon take over that is kind of nice. Takes the cognitive load off of the people developing the applications, and it kind of outsources those concerns a little bit. The cost is a flat rate of 20 cents per hour. So I want to make sure that I'm clear about the distinction here. That is just for operating the control plane. So there's that other component that I mentioned, which were the workers and the minions. That's going to be an additional cost because those are going to be EC2 instances that you launch, and you pay the rate for those EC2 instances. So you can use your reserved instances if you do that. You can use spot instances if you want, but that is a separate cost. The 20 cents per hour is simply to run and operate the control plane. So I did the math. It comes out to about $150 a month is what that costs just for the control plane. So, okay, cost is out of the way. We can talk about the fun stuff now, right? So this is the overall architecture that we have deployed. It looks daunting, but it's not too bad, to be honest. What I'm going to do is kind of break down each of the different components and kind of how we went through deploying this and some of the considerations that we took along the way. So if we strip away a lot of this stuff, we start with the basics, right? This is operating in AWS, which is public cloud. We chose US West 2 as our region. And the first step is to actually deploy the control plane. So there's a number of ways of doing that. You can do it through, you know, the Amazon console, through command line, whatnot. but you provision your EKS cluster, and that's essentially standing up those master components that I had mentioned. When you're setting up your cluster, Amazon requires you to use at least 2 availability zones. I won't get into too much depth about what availability zones are exactly, but essentially it's a way of ensuring high availability of the service. So in order to do that, you specify the subnets and the VPC that you want to use. So you create a VPC, which is your virtual private cloud, which essentially isolates your IP address space in the Amazon public cloud. In our case, we wanted to ensure that the I'll say the attack surface of our backend was minimized. So we've segregated our network into a private and a public network. And the reason that we've done that, as you'll see as I move forward, is only the load balancer is going to be deployed into the public subnet. And that's how we enable the public access from the internet to come into our service. But everything else is running in our private subnets. So all of the EKS workers, all of that stuff is running in the private subnet, and it is not accessible at all from the internet at large. So that's kind of what this level is showing. We have 4 subnets. The 2 on the left are the private subnets. The 2 on the right are the public ones. And again, there's 2 because we have 2 availability zones. So at the next level, we need to actually deploy our workers. So these are our EC2 instances that are actually going to run our application. The way essentially that Amazon does this, it provisions what they call elastic network interfaces, but it's essentially a way for the control plane to talk to your actual EC2 instances, which are the worker nodes running the kubelet that can deploy your pods. Again, these are running in the private subnet because we don't want to allow access to them externally. So how do we actually interact with this cluster? In our case, when you deploy an EKS cluster, you have 2 options for how you access that cluster. So the API server that I mentioned, it can be exposed via a public endpoint. For us being NASA, obviously we don't want to do that. We don't want anybody to be able to go hit our API server, even though they have to be authenticated to actually be able to do anything. We just don't want to expose that. So the solution that we've done is we've taken the control plane and made it private, which means you can only access it from inside your own VPC. So in order to actually get access to that from, for example, my laptop, I would have to get onto a server that's in my VPC. So that's what this one box up here is called, the SSH bastion. You might be familiar with this pattern. It's essentially a jump host where you have to SSH into that host first, and then you can talk to the Kubernetes cluster. So that's where I would run my kubectl commands and things like that. I have to SSH first into the bastion host. The other component up here, the kind of circle component here, is the NAT gateway. That allows the private subnet workers to talk to the internet. So I mentioned the private subnet you can't come into from outside, but we want to be able to access from the private to the internet to download things like updates. If you need to install some software from Yum or something like that, you need to be able to access the internet. So that's what the NAT gateway does. Then we deploy our Elastic load balancers. So this is what's actually going to be allowing the traffic from the internet into our services that are running on the Kubernetes worker nodes in the private subnet. We also have some S3 access that's necessary. So we use an API gateway to allow us access to S3. And then this is just showing some of the routing tables that need to get set up to enable the traffic to go from the private subnet to the public subnet and those types of things. So that's kind of the overall picture of our architecture and kind of why we took those steps along the way. So in terms of authentication and authorization, I mentioned for the API server, everything needs to be authenticated in order to be able to do any sort of work. In AWS, it uses IAM to manage that. There's a connector tool called the AWS IAM Authenticator, which essentially goes and checks with IAM anytime a request comes in. Makes sure that the user is authenticated and will then pass things off to this role-based access control mechanism inside of Kubernetes to see if they have authorization to do the command that they're asking to do. In terms of separation of environments, the way that we did it was we have 3 environments, essentially a dev environment, a test environment, and a production environment. The dev and test environment share some hardware. So essentially we just have like one M5 4X large machine that runs our applications for dev and test. And then we have 2 EC2 instances that run our production software. I'm noticing I'm running low on time, so I'm kind of starting to speed up here a little bit. I'm sorry about that. So one concern that we had when we were going through this deployment is I mentioned the elastic load balancers that get deployed to the public subnet, which essentially exposes ourselves to the internet. Obviously, that's a security concern, right? You don't want anybody to be able to just launch a new load balancer into your public subnet. You need to be able to lock that down and manage who has the authority to be able to do that. So one mechanism for doing that in Kubernetes is to use resource quotas in combination with the idea of namespaces. So essentially we have our application namespaces, which are the dev, test, prod that I just mentioned. And then we have a separate namespace, which houses the actual components that serve the public traffic. And what we do is we use resource quotas to say that the namespace hosting the public traffic is only allowed to have one load balancer. All other namespaces can't have any load balancers. So that's kind of one outcome that we found when we were deploying this. And then one last slide here, kind of getting a little bit into day 2 operations as well as scaling. This is kind of an area of research for us as well, where we have some more work to do. Getting into auto scaling, there are capabilities out there for being able to scale your pods based on the amount of traffic coming in. There's also plugins available to actually scale your worker nodes, your actual EC2 instances based on traffic, and then also scale your pods to serve more traffic as well. So that's an area of interest for us as well. And then also pictured here is kind of the Kubernetes dashboard, which is how you actually get insight into your cluster in terms of what applications are running, what nodes are running, and things like that. So I have a few resources here. As I mentioned, this is essentially the technology that's powering the C-level change portal. The application that we're deploying is the Apache SDAP application, so I have a link there. I do want to point out the read the docs link. This architecture that I'm presenting, it's not out there yet, but I will be sharing all of the resources that I developed to deploy this architecture. So that's the things like the Kubernetes YAML files, the CloudFormation template for actually setting up all those Amazon resources and things like that. That will be shared in the future at that link. And then, yeah, just the link to that blog post that I mentioned, and then the cloud landscape slide, which it's just fun to kind of go around and click on the different things and see what's out there. So do we have time for questions? Okay. Anyone have any questions? Sure. Hold on a second.
I actually had two questions.
Sure.
One is, do you use auto scaling to scale your capacity to resources? And the second was, I saw you had like Nginx components in your diagram, but do you need those if you already have a load balancer that's directing traffic?
Yes, so good questions. So the current deployment, we do have auto scaling groups set up for the worker nodes, but we don't have anything triggering it necessarily. So we manually scale it at the moment. But that's one area that we want to get into, is how we do it based off of some metric. And then your other question. Yeah, Nginx, right. So yeah, I didn't get into super detail on that, but with Kubernetes, the way you expose your services, your applications that are running in the back end, you have a resource called an ingress. And it's just a route that Kubernetes manages. It's a URL path that says at this URL, it's pointing to this backend service. So it uses Nginx essentially to manage those routes. And then the load balancer is essentially just a proxy to the backend Nginx components that are running. Yeah.
So actually, yeah, I had a question about the load balancer too. I'm not really sure if I'm repeating what he said or if I just didn't understand your answer.
Yeah.
But I have another question. I'll ask that first. How long did it take you to do all this, to develop this? So that's one question. And then with respect to the load balancer, it struck me as a little bit odd that Kubernetes didn't actually provide that.
Yeah.
You provisioned that from Amazon as a separate thing. So,
yeah.
So Kubernetes doesn't actually handle load balancing, even though it seems like it would be an integral component in an architecture like this.
No, that's a good question. So to clear that up a little bit, so there is the concept of a load balancer in Kubernetes. And then because we're deploying on the cloud, we rely on that the cloud provider interface to define the implementation of the load balancer. So let me see if I can rephrase that. There exists in Kubernetes an object that's called load balancer. And because we're deploying to Amazon, we configure that load balancer with like Amazon specific configuration options. And then when you create the load balancer in Kubernetes, the backend, the API or the provider interface is responsible for making the AWS calls to provision the load balancer. So I'm not actually going to like the console or the AWS command line and saying create a load balancer. Kubernetes is actually doing that and managing the load balancer for me. It just so happens that the implementation is an AWS load balancer. Yeah. How long it took me? It took a few months. Yeah. I wasn't working on it every single day either. So I mean, depending on how you want to measure time, but yeah, it took a few months. Cool. All right. Thank you.
Okay. Now we have Patrick Quinn. He's the product owner of Cumulus. He's been working within NASA Estes for approximately 10 years, contributing to the systems, including Earth Data Search, CMR, Earth Data Cloud, Gibson the Cloud, and Cumulus. He will be presenting Cumulus lessons learned.
No superlatives for me. I think the cloud meant something different when I was in high school. Alrighty, yeah, so I'm Patrick Quinn. I also want to give a few shout outs. First of all, I have Lauren Frederick up there on the slides. She's here to add a couple nines of availability in case I go down. There's a whole segment of the Cumulus team sitting over there. Wave. There's also a couple on the phone, so they should be waving too. And without them, I think I would not have anything to talk to you guys about. They are the doers. These are my kids. That was just happening this morning. I know you don't think that is as cute as I think it is, but this is my presentation. Okay, so I'm not actually going to talk too much about Cumulus itself in terms of the technologies and how it works and all that. I think we've talked probably pretty extensively over the course of this ESIP about that, and you can certainly ask questions afterwards. But I'm going to be focusing more on the lessons that we've learned along the way. We have a big and diverse team from different organizations working together on this. And we've been doing so for a while and have found some things. So these are the things that today feel like hard-earned wisdom. Don't quote me too.
Speaker, we're interrupting remotely. You're not sharing your slides. Can you turn those on, please?
Yes, I am. I'll turn it off and on again.
And you can see what they see.
Oh. Okay, is it showing now?
Yep, looks good. Thanks.
Okay. All right, so I'm going to start kind of with a little bit of background just so you know what we're trying to do here, and then I'm going to go into some more technical things. So, there we go. So like many people, we are trying to take a data center and move it into the cloud. Specifically when talking about Cumulus, we're talking about the DAX, if you're familiar with that terminology, but the archive centers that hold on to, archive, and distribute NASA EOS DIS data products. Now, in doing this, though, we know that we have actually 4 that we're trying to move roughly simultaneously. So it's a little bit of a different problem from the single migration. We're trying to pull disparate organizations kind of into the cloud together, which is pretty nice because it ends up being a little bit of a reset point where we can look at the way we're doing things, look at common things, and work together to figure out how we want to get things done. And then on the horizon, we see more. So the question is, like, what do we need to do in order to make this successful, avoid duplication of effort, avoid stepping on toes, you know, learn from the considerable amount of knowledge that exists in that bottom row there without losing anything. And so that's kind of the Cumulus space. We exist to move these data centers into the cloud to ingest, archive, and distribute NASA EOS DIS data out of the cloud. So in Cumulus, we have some common ingest pieces, how we manage workflows and bringing data into the system. We manage an archive, so this is pieces like, you know, reporting what we've got, reconciling our holdings, being able to move a file and update our metadata catalog to know where we moved it to, those kinds of things. Operator tooling, so if something goes wrong, someone gets notified and can actually do something about it. A distribution, which in terms of Cumulus, we talk in terms of kind of that first tier distribution of, you ingested a file, we can give you that file back out. And then value add services would be built on top of that, but that's not what we would call Cumulus. So people sometimes accuse me of saying that like everything is Cumulus, so I'm going to call out some things that aren't Cumulus. So truly unique tooling, we rely on the DAX to build that if it's, you know, particular to a data product or those sorts of things. we for our cloud compliance infrastructure, that's NASA Earth Data Cloud platform, some of whose members are here. They deal with things like how do we not overspend our budget and you know, have intrusions and all sorts of networky stuff that I'm not equipped to talk about. Data services, like I mentioned, that's the value add built on top. Operations, we don't operate this, the DACs build it, they operate it. And there's like lots more that we could talk about. So we have started more recently as thinking of Cumulus less as a monolithic system and more of an ecosystem of components. And it's important to call out kind of how the direction that we've been moving here has been to work more with the various organizations that are coming into the ecosystem and bring their components in and be able to kind of have this hub of Cumulus that where the various DACs and our other stakeholders are contributing, participating, sharing what they know. If they have an itch that they need to scratch now, that they can contribute that back and other people can use it. So in doing this, I mean, I think that was one of the biggest lessons that we've learned here is that sharing this separable components is better than trying to be everything to everyone. We're not going to get there, but if we can provide the interfaces and get you 90% of the way there, that's substantial. I'm also simultaneously soul searching on how we do cloud development in general, not Cumulus specific, but I think that there's probably a right place to separate into separate components. And I think if we were to start all over again, I don't know that I would have started with 10 different components. I think it's good and it's healthy for components and microservices and those kinds of things to fall out naturally rather than making work for ourselves. One thing that I guess we try to put out there a lot is that with different organizations, it's actually pretty rare that we see needs that are actually unique. At least when we're talking about moving data around, like lots of people have to move data around, and for our purposes, the protocols that we speak and the types of systems that we need to submit to, that's all common stuff. And so we encourage people to default to seeking out the work of others that have already had to do that legwork to get their thing into the cloud. And the converse of that is that because these needs are rarely unique, if you do find that you're the first one to encounter a problem, you should probably assume that you're not going to be the last one to encounter that problem. Being a big and distributed team, we talk to each other, so you should do that. So we have an agile team. We coordinate extensively on Slack, screen sharing, virtual pairing, video telecons, actually getting together face-to-face quarterly. And on top of that, outside of our team, we have clear avenues for collaboration. So we know how to accept contributions. We know who leads things and how. So big takeaways here are that especially with distributed teams, you just have to be on top of communication all the time. And one thing that we found particularly helpful is that we have these once a sprint, what we call architecture meetings. I put it in quotes because a lot of times it's not about architecture, but very often there will be just some kind of burning topic in development at sprint, and the normal agile ceremonies don't quite take care of it with sprint plannings and retrospectives, but having a forum to have those discussions has proven very helpful. Okay, so enough about people. We'll talk a little bit about how we actually do cloud development. Big thing here is that we have gone pretty much cloud native in AWS. where we are building where possible on top of AWS Lambda and step functions and SQS and all those commonly known pieces. And that encourages a certain way of building things where you're decomposing into individually executable microservice type components. And we test, of course we test, everyone tests. And so we have these unit tests for all the boxes and we can test that our services work. But the big piece here and probably the most complex part of our testing, but also one of the more important parts of our testing is the integration level, where you can test all the boxes as thoroughly as you want, but you need to test the arrows to make sure that your services can still talk to each other and that everything is connecting together fluidly. In our experience, those are the things that actually tend to break, because you're pretty good at making a code change in a small module, but you tend to be pretty bad at seeing the cascading effects downstream. So on the integration testing side of things, we do have a fairly, I want to use the word unique, but I'm sure it's not, a way of writing our acceptance criteria in a language that is can be readily transcribed into tests. It's not quite, if you're familiar with the behavior-driven development and Cucumber and all that, it's not quite that, but each of our tickets comes with a set of acceptance criteria that each one of them can be placed into a test, and it's expected that we have tests for each of those things. At the same time, in the cloud, deploying, running real services is slow. So we do, as much as possible, try to build offline tooling or offline ways of executing things like local stack to speed up development cycles. It can be a little painful sometimes if you have to redeploy between every code change, if you can just get that snappy feedback on your local machine. And then we also have kind of standardized the way that we have written code so that we are able to run the same code. We write code one way that can be written, that can be run in AWS Lambda, but if we need to, for disk space reasons or timeout reasons, we can run that same code in Docker and have a longer execution cycle without having to necessarily choose up front which technology we want to run the code in. We can defer that decision, and actually that decision can be made based on kind of the scenario we're talking about, where in one case it's run in AWS Lambda, but in another case it's going to take too long, we run it in Docker. We have, in building this, Cumulus is essentially a data ingest pipeline on its front end, and it takes data from the science processing system and moves it into the DAC archive system. And in doing this, we have this pipeline mechanism going through AWS step functions. And in order to be able to do that, you have to pass basically all the information that you have to every step along the way. So we end up with messages that you're not even supposed to be able to read that over on the left-hand side, that is describing the resources that are out there in the world that could be used by various steps. It's describing, where the data is coming from and what time it was sent. But ultimately, if you're writing a little service like copy files up there, those are not the inputs or outputs that you want to be speaking. And in order to understand this entire message structure, first of all, it makes your thing too complicated, but it also causes fragility in sort of coupling your tiny little copy files thing to the overall broader message format. If you want to change something in the future, you can't, because everyone in the world depends on you having this complex JSON object. So we have moved towards a model of having explicit, simple inputs and outputs that we feed into each step along the way from that broader message. So in this case, inside of that message somewhere, we have a configuration piece that says basically for the copy files task, we want to pass in an array from here and an array from there that are JSON paths into the overall document. So we're kind of plucking out the primitive pieces of the broader document so that we can pass something much simpler into the copy files task, specifying where to find them. And then the JSON that actually gets passed in is a list of source files and the destination that you want to, the destination bucket that you want to copy them into. So we've gone from very complex inputs and outputs, which are still there, but kind of they're not things that copy files needs to worry about, and we pare it down to something that makes a lot more sense for the domain, and then we're free to change that broader document without breaking everyone in the world. So ultimately that gets sent to copy files. Okay. So I guess another benefit there that I didn't mention is that we can verify which keys it's using and not using. So that can become a big problem if you have a large document and you're sending a lot of extraneous information to a microservice. In order to know what pieces of information your microservice is assuming or depending on or cares about, you're basically cracking open code at that point. Whereas with this kind of mechanism, you can see right off the bat, like I'm grabbing this key from here, and I don't even have access to the rest of the information. So those were kind of general microservice-y development ideas. Moving on to actual specific AWS pieces that we found. One big change that we've made recently that has proven helpful is that we separated out our stateful resources. So we used to have one big deployment that would deploy everything. There are some challenges with that if you want to make impactful changes, like breaking changes to your deployment. You are faced with hard questions about deleting data. Whereas if you have your stateful things, you can keep those consistent in one place, and you can feel free to, alter and evolve the stateless resources because those can be updated without destroying anything. Also, just side benefit is that those stateful resources are very often the ones that take forever to stand up. So if you've ever stood up an AWS Elasticsearch service cluster or domain, it can take like half an hour to stand that up. And if you're doing that as part of a larger template, and you hit an error later in the pipeline, it will roll back that half hour. And so you've just wasted like an hour waiting for this thing to get stood up. Whereas if you can have your, more stateful resources that tend to not themselves break, have them stood up separately from the rest of the stuff, you won't hit that scenario nearly as often. Or you use Terraform. That's just the direction that we've been going lately. We have learned to always queue basically everything. If we care about not dropping a message on the floor, it goes through a queue. So this is what things would look like if you were not using queues. You'd get some sort of external event that says you need to ingest something, and that would kick off a Lambda, and that connection is not guaranteed to actually happen. It almost always will, but you could also have situations where that Lambda just bails because of an exception or something like that, and the message is just gone at that point. And then we have this Lambda that is triggering workflow. So we have an external event that kicks off every once in a while. It says you need to do some ingestion, go start this workflow. Well, that's going to call the step functions API, which itself has rate limiting. So it could very well come back with an error saying you've called the step functions API too many times. And we hit that actually very often as a matter of course if we are doing things like a bulk operation where we say like, okay, do these 2,000 items again. Okay, it will try to trigger them all at once, and you will inevitably hit a rate limit in there and just drop a bunch on the floor. So we don't want to do that. So the solution to that is really to find a way to stick a queue into that loop. So we feed our events into a queue. They get picked up by this worker. If anything fails along the way, then the nature of how queues work is that some visibility timeout happens, and if we haven't acknowledged that we processed the message in that timeout, it will become available again in the queue. If that happens too many times, it'll go to a dead letter queue, but that message is always sitting somewhere for us to deal with. Basically anywhere where you are interacting with an API in a way that you really don't want to fail quietly, we'll say. This tends to be the model that you want. Another lesson learned the hard way. So did you guys know that sometimes data is relational? We have these, it can be tempting sometimes to chase the new shiny object, or to go fully serverless at the time. You know, the serverless database was DynamoDB, and we want to be serverless, so let's go with DynamoDB. Well, you know, it turns out that's not always the best answer for all cases. If you need transactions that possibly span, you know, multiple records, if you're doing things like, you know, complex queries on the data, you know, you want to get date and time ranges or those kinds of things, that those things become a lot harder to do in DynamoDB. So it's just a question of choosing the right tool for the job. And thankfully lately, Amazon Aurora has become serverless in preview, so we can still say that we're serverless without having to take what we'll call a suboptimal database for our use case. That's not to say that DynamoDB isn't useful. It just you know what you're getting into. So this is like I guess an extension of that, which is that you know, a lot of times people will start combining databases. We'll say, well, DynamoDB isn't great for search, but Elasticsearch is. So we'll put the data in both places. That actually works really well for some things like logs or things that you don't really care about being like spot on consistent, but can absolutely be a nightmare if you do care about that. You end up with like crazy synchronization code, basically reinventing transactions outside of your database, which is just don't. And then talk about like how many new services and changes are announced. You have to watch what AWS is doing because it's great. You get to delete lots of code for something that someone else has probably thought about longer. So for us, with just AWS step functions, within 2 years, these things were obsolete. So we had SQS-based workflows that were passing things from one another to one another. We just got rid of that and used step functions. We had something in place to poll for activities on waiting to be run within our step functions, but AWS got rid of our need to do that. We needed to add components in place to be able to deliver messages to SQS. No longer need to do that. You can delete that. That whole massive input JSON to smaller document mechanism that I was showing, we had to put together a pretty massive thing to be able to do that before, and they just allowed us to do it via config in the step function, which is pretty nice. The ability to iterate over lists, you can also just kind of do that now, whereas we had to do some crazy things with child workflows and monitoring and all that. So, you know, the big takeaway there is that you should keep an eye out and keep on top of things because it seriously helps. That is all I have. Any questions? Hi, Joe.
Hey, so could you go a little bit more into the mechanism of how you share the code between a Lambda function and a Docker container? Like, is it originally on the source control and you sort of grab it at
No, so we have
creation time?
we've created a little Docker container. It's not particularly complex, that is able to, it'll look at the definition of your Lambda. So you pass to the Docker container the ARN of a Lambda. It looks at that. It looks up the code that runs in that Lambda, grabs the zip file, and executes it as AWS Lambda would. So it's, I'm sorry, I didn't catch that.
So you're using your Lambda function as a source of truth of the code?
Yes.
Okay.
I mean, so the reason for this in our case was that most things were Lambda, almost everything was Lambda, but occasionally we would need something that had been a Lambda to suddenly not be a Lambda because of disk space or memory or whatever. So we had that, mechanism to kind of pull it out.
Thank you.
Thanks. So in terms of the next steps, I mean, basically you have the capability to ingest files and store data. Where do you think the next big chunk of work is in this?
So I think, we hear everyone talking about this, problems with data preparation versus analysis. And my understanding there is that much of that is in the sort of services / data harmonization sphere. That is going to be a tough nut to crack, though. So we'll see where that goes.
Do you have any rules of thumb as to when you would use Docker or preferred Docker versus Lambda functions?
So I think it's a tough call because the lines have gotten blurred a little bit too lately with AWS Fargate, where it used to be that if you wanted to run Docker, you needed to have like EC2 instances up that you could throw Docker at and all that. And so you still have servers to manage and all that kind of thing. Now you can do it more serverlessly. So it's, in those cases, for AWS in particular, I would tend to look at sort of the length of execution, the amount of control that I need over where the code is executing, and latency needs, and usually probably also cost. Fargate and those sorts of things tend to cost more if you have shorter lived invocations and possibly higher latency in doing those. So kind of let the technology guide which one was right or wrong. Also, I guess on the Docker side, that's assuming that you could run them in both places, but there are many cases where there's something that you just either can't, or it would be like a relative pain in the neck to be able to run something in AWS Lambda, like if you had some random Fortran utility that you wanted to run on a piece of data.
Does this work? Okay. So to just be crystal clear, you're not dynamically choosing whether to invoke a Lambda or a Docker with a Lambda input at like execution time. It's something that you're like, okay, every time you do this, use Docker. I mean, is it like an implicit configuration step that has to be set up a priori, or is it dynamically done?
Yeah, I mean, so I've thought about how to do it dynamically, and you could, but at that point you have to be able to estimate how long it's going to take, or whether you're going to exceed the limits that are going to cause you to hit that, and we just don't need to do that. So no.
So as we make this copy of convenience in the cloud, are we looking at restructuring the data at all to make it cloud optimized, such as rechunking? Is that part of the process?
So I'm not sure the answer to that question, but Cumulus itself is not the copy of convenience. It is the copy record.
I think
Or not
I think
intended to be?
I don't think you want to speak for all of Estes in that.
Okay, fair enough. We can talk later. Or rather, you can school me later. Thank you all.
All right. So we will hopefully try to make room for other questions. I know you had one more question at the end, so I will do my best to stick the time. No promises, but I'll do my best. So I'm Namrata Malaraut. I'm from Jet Propulsion Laboratory. I've been there for a little more than 3 years now. My current work ranges across a mix of research projects like MAP and ARIA and mission work like SWAT and NISAR. I'm one of the core developers on HiSDS, and I work with a group of very talented and brilliant people to create adaptations and adopt it to such mission work. So I'll be talking about cloud-based data processing and workflow systems. So how many of you are familiar with HiSDS? All right, cool. So I'm going to start off with the brief introduction. So HiSDS stands for Hybrid Cloud Science Data System. It gives you the basic set of SDS services of resource management, data discovery, workflow execution, and then the corresponding interfaces to interact with these services and a set of APIs. And it's designed to run on a combination of on-premise and cloud infrastructure, hence the word hybrid. So I'll get into how we do storage and data processing in a bit. So for running in a cloud environment, the infrastructure itself needs to be resilient and fault tolerant. So I'll cover that in some of our lessons learned and the steps we've taken to accomplish that. We do utilize spot market for cost effectiveness when it comes to large processing requests. And we run our executables, PGEs, in Docker so that we can easily scale in and out using autoscaling. And this SDS allows for triggering of jobs as well as on-demand requests. So kind of jumping into the top level software components here. We've got external data sets, ancillaries that we need to get into our system, and then we have on-demand requests coming from our users into our system. So that's SDS. And it orchestrates our PGEs in the form of Docker, like I said. We run on compute instances. Sometimes we like to do a combination of on-premise machines as our workers, as well as auto-scaling. And we push the products produced onto S3 storage. So the SDS is composed of mainly 5 components. We have the resource management that is responsible for orchestration of jobs and maintaining the health and status of the jobs in our system. We have discovery services, which is essentially our metadata catalog for the products. We have a metric system to collect metrics both on things like CPU utilization and memory, as well as since we're using cloud, we want to keep track of what instance types are we utilizing and what are the number of jobs coming through our system at a certain time. And then we use continuous integration. So we've been using Jenkins to automatically build our PGs, which are best practices. We like to have them version controlled. So with the autoscaling, we like to set up policies to limit the size of how much we want it to get to because billing. So we like setting up target tracking to do that. And our metric alarms are based on our work queue size. So based on how many we're getting in our system, as more and more jobs get queued, we want them to crank through faster, so we want to be auto-scaling. So this is from our metrics dashboard. So this is a very classic example of scaling out once we have a huge volume of jobs. Whereas the second one here is more interesting. This is with manual intervention. So as you can see in the beginning, not a lot of jobs are going through. This was actually during our OCO2 reprocessing campaign. So we identified the bottleneck and figured out that it was one of our compute instances. So what we decided to do is set up an auto-scaling group, which basically had workers on them listening to this queue. So immediately you can see the huge increase in the number of instances here. So I think our max, we scaled out to about 8,300 nodes with 32 cores each. So that's about 250,000 or 260,000 cores at one time. Now, HighSDS is designed in such a way that it's a fabric. We wanted to have our choice among the diverse cloud vendors. So to enable that, HighSDS is more, you can think of it as a fabric. It goes on top of the cloud infrastructure, and then everything else interacts with HighSDS. So we've been running with OpenStack and Amazon Web Services largely, but we have put up an instance of HighSDS prototyped in GCP and Azure. Now, when it comes to deployment, this is what our current process is. It has evolved over the years, and this is most definitely less painful than it used to be. Our first is, of course, our SAs help set up our accounts and our resources like the S3 buckets, the IAM accounts, everything, and the AMIs. Then the deployment engineer, we use Terraform to stand up all of the PCM instances. Then we log into we like to have one specific instance that is dedicated to orchestration. And we have a command line tool called SDS CLI, which lets us deploy all of the adaptation to the various instances and have our code bundles uploaded onto we have a dedicated code bucket, so we're using S3 for that. So when we autoscale, our workers can pull down the code bundles directly to execute them. So here is the list of HighSDS adaptations. So currently in progress, we've got NISAR, SWAT, SMAP in the cloud, and Aster. We've done the OCO2 L2 full physics processing. We have a third reprocessing campaign of that coming up. Getting ready for NISAR, ARIA, and the measures project. Now, HighSDS allows for us to concurrently run different types of pipelines within the same cluster. So we can do keep up, so near real time, continuous monitoring and cranking out of products, bulk analysis, so on a request or like a bulk reprocessing campaign. Then we've got urgent response. So like in case of ARIA, whenever earthquakes happen, our system automatically jumps into action and our pipelines are automatically triggered. And then we have on-demand analysis. So based on requirements from scientists, we do process. Now, when it comes to these processing pipelines, the PCM supports two types of workflows. We like to distinguish them into explicit and implicit. So explicit is, we do have a sample a workflow executor within HighSDS called SciFlow. So it allows you to do the sequential step-by-step linear workflow, as well as you can branch out with the MapReduce style. And we like to run our workflows in nodes for scalability. So it's not that the workflow orchestrator is sitting on one machine trying to orchestrate different jobs and different steps. The workflow itself is running in one instance. So this allows us to scale very efficiently. Then we have implicit workflows, which are trigger-based. So you can think of this as AWS step functions, essentially. So we have event-based triggers. This can be from outside of the SDS. For example, S3 events. If something is uploaded or deleted from an S3 bucket, it can trigger some processing in the SDS, and I have an example of that coming up. Then we have database triggers. So this is anytime a data set is created, we can set up rules that says, oh, hey, when you see like an SLC coming into our system, why don't you run this evaluation? So that is very powerful because it allows users to put together a workflow without writing a single piece of code. And they can just do that by constructing these queries. And we have a faceted interface, which allows users to figure out their criteria, drill down to what subset they like, and then with a click of a button, they can choose which type of PGE they would like to run. And so this is the process they can do both for on-demand processing as well as set up your rules so that whenever something that interests you is coming into our system, we can process it. So the first example I'm going to show you is a data-driven workflow. This is an example from ARIA, from our standard products pipeline. So first off, we're starting with our ancillaries coming into the system. So we have scrapers running to get acquisitions and orbits into our system. We have areas of interest set up. So we know which which acquisitions these areas of interest would intersect with. So for every single area of interest, we run what's called an enumerator. What it does is looks at our system, sees which acquisitions are available, and then it applies masking on them to see which ones would actually be relevant to the processing pipeline downstream and eliminates the rest. So it then publishes an acquisitions list and an acquisition audit trail. The audit trail is useful because sometimes scientists go ahead and do their own processing by hand and say, my results don't look like yours. What did you do? So that's where the audit trail comes handy because we can explain which acquisitions were used, which weren't, and what was the reason for them. Now, once we have an acquisition list, it says that it automatically triggers a localizing step. So The acquisitions are just metadata. We're not downloading the SLCs beforehand. And only when we have the acquisition list, we know which SLCs we actually need in the system for the processing. So the SLC localizer submits another job, which is the actual download of the SLCs. Now that we have the SLCs, now this is a data set, this is going to trigger an evaluation. What this does is looks back at the acquisition list that was published before and says, is everything in that list now in the system? If it's in the system, it means we're ready to run. So that puts out a configuration file. Now, this configuration file is used by, we're using ICE, the topset PGE, to produce geo-unwrapped interferograms. So that configuration goes into the PGE. We have our gun, well, unfortunate name, but it's called the GunW. And once that is published, we now want to see, are we ready to push this out to the DAGs? So what we are doing currently is doing an analysis of, do we have completeness? So from scientists, we have learned that it's sometimes not useful if you just keep pumping out all the products you're producing to the DAG. What they're interested in is, do I have complete coverage? So because of that, we have decided to create a track list, which says, for this area of interest, for this specific track, these are all the products that are available, and we are assuring that you have full product coverage for that. And once that track list is published, it kicks off our product delivery pipeline. And okay, this is a very simplified version of our standard products pipeline. If you're interested to dive into it more, you can enjoy all the spaghetti and the meatballs over there. Yeah, feel free to dive into this at your own time if you'd like, and shoot me any questions. Now going into mission adaptation. So I'll give a very high overview of what we're doing here. So mostly our missions are kind of when they're locked into AWS. So first, so we've got our PCM running in the SDS. The GDS stages something in our incoming bucket, which then triggers our ingestion process. So this is an example of an external event triggering something within the SDS, right? So we have dedicated ingest workers, which are going to go ahead, extract the metadata, publish the metadata into our data store, push this product out to S3. There you go. So it becomes an S3 data set. So our L0s are staged as data sets. Now, once we have our L0s, we're going to start kicking off our processing. So we have dedicated compute workers based on PGs. Our best practices is we like having a one-to-one relationship between our auto-scaling groups and the type of PGE that we're running. Once our PGE execution is done, we, again, same process. We're going to push the metadata to our internal data store, which, by the way, we're using Elasticsearch to maintain our metadata store, and we're pushing our products out to S3. Once we're done with that, we would want to deliver our products out to the DAGs. So the staging of these products is going to trigger our delivery workers, and then we go and host them to the landing zone for the DAG. So now we'll talk about the workflow executor site flow. This was first prototyped through SMAP in the cloud effort. So we came up with this generic framework for PGE execution. We wanted to break it down into 3 basic steps. The first is the pre-processing. So evaluate all of your preconditions and query based on your selection rules what the input ancillaries need to be. And we create a configuration out of that, which is called the run config. After that, we want to execute the PGE. So now keep in mind, this is the workflow that is running in an autoscaling instance. Now, for the PGE execution, it is going to farm that job out to a different worker. It'll wait for that job to finish. So there are different modes. You can either do synchronization, so you can wait for the status of that job, whether it was successful or not. But in our case here, we are chaining a couple of PGs together, so we want to only move forward after that has finished. Now, when it finishes, or whatever its status was, it's going to come back to us, and we do a post-processing step. So this does a check on whether or not the PGE has successfully completed. If it has completed, then what is the information that the next one needs, right? Which metadata fields does it need so that the next one can do its preconditions? So we do that step in the post-processing. So with these 3 steps, what we've realized is we can chain together as many PGs as you want, or you can break it down. You can have dedicated workflow jobs per PGE, and I call it a workflow because of these 3 steps. And this really, I've noticed that this came out of the missions, but even for ARIA, the preconditions is very helpful because it minimizes the time it takes you to unnecessarily localize a lot of products into your work directory for the job and then figure out what you need or try to mine out the metadata. Instead, just query the metadata based on the selection rules you already know and put out a configuration and just use that to kick off your PGE. Now here's the product delivery mechanism. So within our PCM, we've got our metadata catalog and the resource manager. When our compute workers are done executing and our data sets from our buckets are ready to be delivered, what we do is we start up our delivery workers. So the worker is going to pull that job from the resource manager. So the way this works is the autoscaling workers are listening to a specific queue, so they pull the job, right? So they pull the job and it creates a message that is sent to an SNS channel. So the DAGs are subscribed to this SNS channel. So it goes into a queue. So as they get more and more products being delivered from our end, they start processing them one by one. Once they have processed that, they give us back a message, which is the handshake, to a separate SNS channel that we are subscribed to on our end. And we have a Lambda listening to this channel because we want to register whether or not our delivery was actually successful. So this actually kicks off a job that is going to basically stamp our product saying, was this successfully delivered or not? Sometimes there are failures. For example, for Griffin, we work with ASF, and sometimes we get failures where, unfortunately, the object isn't available anymore on the S3 bucket where it was supposed to be because it was purged. Or the metadata, they have their own schema validation on their end, so they do validate our metadata to make sure that it meets their standards for quality of product. So yeah, that is very important for us to keep track of. And we also like to maintain timestamps in our system for latency, right? When did we send out this message saying that we're sending this out for delivery, and when was it actually ingested into the DAC? So we do update our metadata catalog with all of that information after we receive the handshake. Now are we going into our challenges and lessons learned. Cost optimizations when it comes to storage. Of course, we use the lifecycle rules on buckets, but I think when it comes to our processing, one of the biggest things that we have learned is only store the metadata first and then figure out what you need only then go and download those products. And this applies for both upstream ancillary downloads, like downloading SLCs. I'm only going to download them if I know that it's going to be used for monitoring one of the areas of interest in our system. If not, why bother? I have the metadata related to it. If I need it, I'll know and I'll go download it. And same applies for our intermediate selection logic, right? So you query the metadata and figure out which intermediate product you will be needing for your next step. Then the job itself can localize those from S3. So the part that I said about SLC is what we call our network enumeration logic. And we only store what is hot. So we have a rolling archive. So in case like Griffin, we are pushing out our products to ASF. So if they are not recent, if we are not currently using them, we are going to remove them from our storage because the DAC has it. Optimizing the scaling in and scaling out. So there are major cost savings by using spot instances. So by 75 or 90% versus using an on-demand instance. So AWS does terminate the compute instances if the market prices exceed the bid threshold. So at that time, we end up with terminations. So it is better to scale up in group sizes across multiple availability zones so that we can minimize the chances of getting terminated when they rebalance their load. For scaling down, always use policies which is suitable for your system, like CPU or network utilization. For us, it is the size of our queues. And the highest DS instances have a system called Harikiri, which is self-terminating. So this is domain knowledge. They are self-terminating instances. So if it's hanging around for about 10 minutes without picking up a job, it will terminate itself. The thundering herd. So when you have such a large system with thousands of nodes picking up jobs and continuously communicating with your SDS, you are going to end up with a lot of requests hitting the same API over and over again. So rate limit your APIs and introduce jittering into your API service so that it's not overloaded and doesn't go down. And best practices on development end is to have backups on your API requests and to have, you know, a good protection in case of failures and retries. So those were the main lessons learned. HiSDS is an open source project, so I've provided the links to our wiki, our issue tracking. The wiki and issue tracking are fairly new. We are working on migrating out all of our documents from internal JPL to public, and that is our GitHub repo. Are there any questions? I know I rushed through it, and that was a lot, but questions?
So you mentioned that HiSDS was open source. Is there anyone outside of JPL that you know of that's actually using it?
Yeah, so we have EOS at Singapore, the Earth Observatory system. So they are doing a version of ARIA for Southeast Asia. They are working with all of our public code right now, and they are running full-fledged processing.
Okay, do you know if they have any plans to enhance and then feed back into the main base?
They already are.
Excellent.
We've been getting contributions from them, with it, which has been great. They've been improving our code. All right, well, I think we're actually over time. So if you guys have more questions, feel free to come up here and talk to us. All right, thanks everyone.